Electromagnetic waves. Vocabulary. Electromagnetic waves. The electromagnetic spectrum. Speed of light equation. Roy G. Biv. Hi, this is Ben Gearing. Today we're going to talk about electromagnetic waves. Remember, all mechanical waves, which were transverse or longitudinal, require some sort of medium to travel through. So they had to have a medium in order for the wave to travel through. Electromagnetic waves are waves that can travel without the use of a medium. So they can just travel through even empty space. My limited artistic abilities can draw a mechanical wave. I can draw a transverse wave. But I'm not good enough to draw an electromagnetic wave. So this is what an electromagnetic wave looks like. And if you'll notice, it's two transverse waves working together. So the wave that goes vertically, so this wave is our electric field, and the wave that propagates horizontally is our magnetic field. These two fields work together, which allows them to travel through empty space. But aside from combining electric and magnetic waves, electromagnetic waves share the same properties as mechanical waves do. As shown in the picture, all the waves still possess a wavelength, much like our transverse and longitudinal waves. Differences in wavelength also allow electromagnetic waves to be classified. And this is where the electromagnetic spectrum comes into play. Electromagnetic spectrum. Man, that's a long word. So within this spectrum are all the kinds of electromagnetic waves that we know. And some of these may sound very familiar to you. Things like X-rays, radio waves, or how about microwaves? Yes, indeed. These are all on the electromagnetic spectrum. And here it is. So this is the entire spectrum from front to back. And electromagnetic waves range in size from 100 meters down here to a size as small as the nucleus of an atom. Within this spectrum, we can and do, or also within this spectrum is my favorite, visible light, which allows us to see. This is one very tiny portion of a large spectrum. And the waves, even within our visible light, have different wavelengths. But the first thing we need to look at is how we can understand and determine all these things. So first things first, the speed of light is constant, whether it's visible light or one of these other forms. The speed of light is 299,800,000 meters per second, or 2.998 times 10 to the 8th meters per second. For this course, we're going to call the speed of light 3 times 10 to the 8th, or 300 million meters per second. Just to simplify things a little bit. This will be an important number to remember as we work through the equations we'll use to determine frequency and wavelength. We've already talked a little bit about wavelength and how it varies between different waves in the spectrum. But how does frequency come into play? Initially, we learned that frequency is equal to the number of waves that pass a point in a second. But now that we know how fast these waves are moving, we can use an equation, and instead of counting the number of waves that pass a point, we can calculate the number of waves that pass a point. The equation used for this is the speed of light equation, which most of you have seen, and it's c equals, some of you have seen maybe, frequency times your wavelength. Remember, wavelength is symbolized by the Greek letter lambda, which looks like an upside down Y. So let's practice this quick and find the frequency of a wave that has a wavelength of Let's practice this quick and find the frequency of a wave that has a wavelength of 1.6 times 10 to the minus 9th meters. So our wavelength is 1.6 times 10 to the minus 9th meters. And we're going to try to find the frequency of this wave. First thing we need to do is take our equation, which we said was the speed of light equals frequency times wavelength, and we need to manipulate it to find our frequency. So our frequency is equal to c, which is the speed of light, and divided by our wavelength. And the next step in this process is to start plugging in our numbers for the equation. So I have my frequency is equal to 3 times 10 to the 8th meters per second. I divide that by 1.6 times 10 to the minus 9th meters, which we got from right here. And I come up with an answer for my frequency of 1.875 times 10 to the 17th hertz. Just like with mechanical waves, the relationship between wavelength and frequency is inversely proportional. So in C equals frequency times wavelength, C always has to equal 3 times 10 to the 8th. So if our frequency increases, our wavelength has to decrease in order to keep this number the same. This equation can show us the difference between various waves in the electromagnetic spectrum, but it can also show us the difference between the light that we see on a daily basis. So if we go back to this, we can see that our red light and our blue light have different wavelengths. So our red has a wavelength of 700 nanometers, and our blue, our violet, has a frequency of 400 nanometers. If we think about the colors in the rainbow, we notice that the orders of the colors on this spectrum, so these colors here, fall in order. So we have red, orange, yellow, green, blue, violet. If you've never heard of the acronym before, you will today, and it's Roy G. Biv. So we have red, orange, yellow, green, blue, violet. It used to work a lot easier when they had indigo still in there, but they took that out. So now it's just Roy G. Biv. We start with red. So if I asked you a question and I asked you which had a longer wavelength, orange or green, sit and think about it for a second. And I want to know what you come up with. Orange or green, which has a longer wavelength? And if you said orange, you're absolutely correct. Looking at this spectrum, we see that orange has a wavelength of about 600 nanometers, 650, somewhere in here. While green has a wavelength of between 5 and 600 nanometers, so about 550. So orange has a longer wavelength. This has been Ben Gehring. Have a great day.